Hello there, Mr. Sutton here with the AB Calculus 4-1 Extra Practice Number 1 solutions on extreme values of functions. For this calculator-based problem, we want to locate the extrema of this function here on the interval from -3 to 1. So we're basically going to test out the endpoints along with critical values and see what gives us the highest and lowest y values. So let me start by getting y prime out of this. And we'll just call that f of x. All right, there we go. So f prime then, we've got 3x squared plus 2x minus 8. And you have to do this before you can just set this equal to 0 and solve it on the calculator. Whenever you use the derivative in an equation, you need to show algebraically what it actually is. So let's plug this in our calculator now. So there we are. I've got it in my y1. And for my window, I'm going to go between -3 and 1. Then let me do a zoom 0, zoom fit. And we'll see what the x-intercepts are. So we've got one x-intercept right here. This looks to be -2, but just to be on the safe side, since I've got a calculator, let me do second trace, option 2 for zeros. And let's move my spider a little bit to the left of that. And then a little bit to the right. Press enter one more time. Yep, it is -2. All right, so that happens at x equals -2. That is a critical value that's on our interval, so we have to test it. Let's test that now along with -3 and +1. So testing out -3 first, and again, I can use the calculator for this. So let me I have to enter the original in my calculator to do this, though. So going to y equals, I'm going to put this in y2, and I'll just do it off camera. There we go. Original function, f of x, entered as y2. Quitting out of there now, let me do alpha trace, and then select y2. Enter, and let's plug in -3 for that. That comes out to 11. So 11 is the winner for whatever race is going on because it's the only candidate right now. Let's try out -2 as well. That's the next value there that we need to test. So going back to the calculator, I'm just going to yank my input from before, and I'm just going to replace the -3 with a -2. Enter, 17. Okay. And now we also have to test out the other endpoint 1. Plugging that in, it looks like that's going to come out to -1. So at the end of the day then, -1 is the absolute min and 17 the absolute max. For this problem, we're trying to find the absolute extremes. We'll start by taking the derivative to get some critical values to test out. So our first derivative, that's going to be 1/2 times all this stuff to the -1/2. Times the derivative of the inner function using our chain rule here. So we have a tail of 7. And let me just clean this up a little bit to make it easier to work with. So this is going to be 7 over 2 radical 7x plus 7. All right. So we're going to look for critical values. Those are places where f prime here is either 0 or undefined. This expression, since it has a constant in the numerator, a non-zero constant, this is never going to be able to equal 0. However, it is going to be undefined at x equals -1. Unfortunately, -1 is not on the interval from 2 to 4, so we can't count that critical value. I guess it is fortunate because we don't have to test it. So we can say then that there are no critical values between 2 and 4. Even though there might be critical values out there, there's none that are actually between 2 and 4. So we just have to test 2 and 4 now. Let's do f of 2 to start with. So that's going to be the square root of 7 times 2 plus 7. That's just the square root of 21. We also need to do f of 4. That's the square root of 7 times 4 plus 7, so that's 28 plus 7, or 35, square rooted. And now between the two of these, 21 square root is going to be lower, so that's our absolute min. And then absolute max is the higher one, radical 35. To find the absolute max and min for this function, we have to test out the endpoints along with critical values. For critical values, let's find f prime and see what zeroes this out. So my first derivative is going to be 3x squared minus 12. Setting that equal to 0 and solving now, if we factor out a 3, we've got x squared minus 4. And then splitting this up, this is x plus 2, x minus 2, which gives us critical values of negative and positive 2. Now, only positive 2 is actually on the interval they gave us between 0 and 4. So that's the only one we're actually going to have to test out between the two of these. We also have to test out 0 and 4, though. So testing all of those out in f of x just to see which one gives us the highest and lowest values. F of 0, that zeroes out everything in the original. That gives us just 0. F of 2, that's going to be 8 minus 24, so that's going to be negative 16. And then finally f of 4, that's going to be 64 minus 48, which is going to be positive 16. So between these, negative 16 then is our absolute min, it's the lowest value, and 16 is the highest value, so that makes it our absolute max. On this problem, we're trying to find absolute min and max for this rational function. So we can definitely know we have to test the endpoints of 3 and 6. We also need to test any critical values between 3 and 6. To see what those might be, let's find f prime. So in order to do this, I'm going to need to use the quotient rule, u prime v minus uv prime over v squared. Let me set up my box and ribbon to start that process. So I have my numerator, x squared, denominator, 2x minus 4, and their derivatives, which are 2x and just plain old 2. Using the ribbon to multiply all that out, I've got in the numerator 2x times 2x minus 4 minus 2x squared. And then down below we have 2x minus 4 quantity squared. So I need to figure out where this thing comes out to 0 or undefined. Let me start with the 0 end of it here. So to get that, I'm just looking to see where the numerator is 0. So let me distribute this out. We've got 4x squared minus 8x minus 2x squared equals 0. So this is really 2x squared minus 8x equals 0. I can factor out a 2x, leaving me with an x minus 4 inside. And then they see that this is going to equal 0 if I have x equaling 0 for that 2x piece, or if x equals 4. Both of those zero out this equation. Now between the two of these, only 4 is actually between 3 and 6. Now there is one other critical value that might come into play. Looking at my denominator here, an x value of 2 would make this denominator 0, which would make the derivative undefined, which would give us another critical value. But 2 is not between 3 and 6 either. So we actually don't have to worry about that one. At the end of the day, the only critical value we end up needing to test is 4, because that's the only one between 3 and 6. So this DNE x equals 2 doesn't count. So only x equals 4 is in the interval. Let's test that along with 3 and 6. So f of 3, that's going to be 9 over, let's see here, this is 6 minus 4, so 2. So 9 over 2. Now let's test out f of 4. That's going to be 16 over, this is 8 minus 4, so 16 over 4, which is 4. And I am going to simplify these when I can, because I have to compare them to see which one's bigger and smaller. That's easier to do if I've got them simplified. And now I also need to do f of 6. So that's going to be 36 over, this would be 12 minus 4, which would be 8. So 36 over 8, we can reduce that by 4 to become 9 over 2. So this is kind of interesting. When the dust settles, we actually have 2 absolute mins. Both of these 9 halves here are tied. And then 4, bigger than those ones, is going to give us the absolute max. To locate the absolute extremes for this function, we're going to eventually have to test the 0 and the 2 for the endpoints, and whatever critical values we get when we take the derivative and figure out what zeros this polynomial out. So starting with that derivative then, we have negative 3x squared plus 6x, and this last thing just becomes 0. Setting this equal to 0 and solving, I can take out a negative 3x. That leaves me with an x minus 2 equaling 0. So this is going to happen when x is 0 or positive 2. Those are the things that zero that out. Those just so happen to be the actual endpoints. So I guess one way or another we're testing out 0 and 2. F of 0, that zeroes out everything in the original except for negative 3. F of 2, that's going to give us, let's see, negative 8 plus, this is 3 times 4, so 12 minus 3. Well, this is really negative 11 and 12, which is positive 1. So then negative 3 is our absolute min, positive 1 is our absolute max. To find the extremes for this function, let's start by taking the derivative. So that's going to be, let's see here, 4 times 1/2 is 2, so 2x cubed minus, this is going to be 12x. This 8 gets zeroed out. And I need to find critical values where this is either 0 or undefined. It's not undefined anywhere. It's a polynomial. So that means we're just looking to see what zeroes this out. I can start by taking out a 2x. That'll leave me with an x squared minus 6. And if 2x equals 0, that means x equals 0. So that's one of our possible critical values. And then in here, if I add the 6 and square root both sides, I get plus or minus radical 6. Now, out of all these critical values, which ones are actually in this interval? Well, definitely 0. That's between a negative and a positive. Negative radical 6, that's somewhere between negative 2 and negative 3. So that's definitely in this interval. Positive radical 6 is somewhere between 2 and 3, so that's not inside this interval. So only 0 and negative radical 6 need to be tested because those are the only ones in the interval they gave us. So going through and testing all of those out without a calculator now, let's start by doing f of negative 5, which is going to be all sorts of fun here. So negative 5 to the 4th, that's 625 over 2, because we had the 1/2 out in front. Next, we have, let's see, negative 5 squared is 25. Negative 6 times that is negative 150. And finally, we have that negative 8. So doing some mental fraction math here, 150, we can treat that as negative 300 over 2. 625 over 2 minus 300 over 2 is 325 over 2. And now 8 is really 16 over 2. 325 over 2 minus 16 over 2, that's going to be 309 over 2 for that final thing, which is about 150 and some change in terms of comparing it to other numbers. Next, let's do f of, let's see here, we need f of negative radical 6. That would be the next most positive number. So that one's actually not so bad. Negative radical 6, if you raise it to the 4th, you're basically doing 6 times 6, because you're doing this thing squared times this thing squared. So that's just 36, but we're taking half of that, so that's 18. And then radical 6 squared is just 6 times 6 is 36, so minus 36 there. And then finally the minus 8 at the end. So let's see here. We've got negative 18 minus another 8 is negative 26. And then we have to test out, let's see, what else do we have to test out? 0. Oh, gladly. F of 0, that zeroes out everything except the negative 8. I almost wish I could test that again, but we got to move on to the next number. The next number's not so bad, 1. So that's going to give us 1/2 for that first number, minus 6 minus 8. So let's see here. This is 1/2 minus 14, which is 1/2 minus 28 halves. That's negative 27 halves. Comparing these now, the absolute min out of all these, we have 3 negative numbers to choose from. Negative 26 definitely beats out negative 8. Negative 26 is also going to beat out negative 27 halves. I mean, this is like negative 13.5. So this is our absolute min right here. And 309 over 2, I mean, we can, hem and haw over what it is exactly, but it's the only positive number. So it wins absolute max out of this lot.